So hi, myself Shraddha Agarwal. I am going to talk about the DMA-based example design that is from the Xilinx for the Vivado version 2019.1. So the main objective is to verify the working of the design for the different sampling frequency rate and also to capture the large amount of samples at the ADC using the DMA design. So in this design, I am using the PSDDR memory that is used for playing and capturing the data to the DAC and ADC in, and DMA is used in between to for the memory transfer to and from the data converter. So in the DMA can use the DMA in the two mode, that is in the simple mode and scatter gather mode. For this design, we are using the DMA in the scatter gather mode. So for the design setup, we are setting the DAC and ADC clock sampling rate at 1.47456 GHz. MATLAB is used to generate the input waveforms of the DAC and to read the output received from the ADC end. So for the different sampling frequency rate, we are using the TICS Pro software to generate the clock files. So as we discussed in the loopback design. Now coming to the block diagram part. So you can see here we have a 4 GB DDR memory, then that is connected to the DMA. So DMA, and then in between we have a clock conversion IP that is being used if required. Then it is connected to the RF data converter, that is a DAC. From the DAC we are connected through the loopback, that is coaxial cable, DAC to ADC, and from the ADC we are receiving back to the data via DMA to the DDR memory. Now this is my Vivado block design. So this is the RF data converter that we are using, that is USB RF data converter. And then you can see here DDR memory is connected to the AXI DMA DAC. Scatter gather mode is activated as we are using the DMA in the scatter gather mode, and then FIFO buffer is in between, that is streaming the data from DMA to the RF data converter, and then at the output only we have a stream data FIFO, that is streaming output data to the DMA that is written back to the PSDDR memory. Moving forward, for the design setup, we need to have a input signal that is we are generating through the MATLAB files. Then what we need to do first, we need to open the Vivado project, extract the zip files that we have, then open the block design in the Vivado. We need to first set the required sampling rate at which we want to make our design work. So this is ADC 224. Right now I'm using a DAC 229. I'm using for the design. So we need to put the required sampling rate over here. And then you can see the output fabric clock will generate it. That is the AXIS clock we are using for both DAC and ADC. That is set to 184.320 MHz. For the different sampling frequency rate, we need to insert that clock files in the clock files folder that we have. So first we need to generate the required set of registers value from the TICS Pro software, and then we need to export that file, and then we need to put that file in this folder. That is, we are having a clock files folder where we can put that register generated file. Then we need to generate the output product followed by the design wrapper and bitstream. After that, we need to export the hardware and then launch the SDK. After launching the SDK, we need to import the SDK project files and generate the BSB sources. Now, I will talk about the design setup. So this is my design setup. Here you can see through the external coaxial cable, I'm connecting a tag to the ADC port. That is like a loopback. Here this is the power cord connector, this is the switch, and then this is the cable, JTAG cable that I'm connecting to my laptop system. So now in this video I'm going to talk about how to run the design. So this is my SDK window. So what you need to do first, you need to go to the Teratom window. So go to the search and go to the Teratom window. Then select the serial port. Then change the speed to 115200. That is set the baud rate as required. Then confirm the new settings. Then again go to the SDK window. Click on the run configuration. Then launch on hardware. So as you can see, once FPGA will get programmed, message will appear on the Teratom window. So it will take few minutes to get programmed. Then you can check the message on the Teratom window. So here now you can see FPGA's program and you can see the message like IP version will appear on the screen. Then it is configuring the clocks. That is, we are having a reference clock set to 122.88 megahertz, and then sampling clock is set to 1.47456 gigahertz. That is for the same DAC and ADC. That is configuring in the progress right now. So after configuring the clockwise, different commands will appear on the screen. You can use this command to set ADC tag status, calibration details, power on status. So you can see over here, we have a different commands that we can use to check the status of my ADC and DAC port. So here you can also see DAC sign and DAC play that is used to play the waveform to the ADC that we will discuss later. Now, what we need to do, we need to go to the uh, folder where we have a output data files. Now, you need to change the directory from the XSCT console. Go to the change directory, enter the desired file location, then go to the MATLAB and generate the input waveform. So here we set the waveform name is tag output square dot bin. So after generating the files that you can see, generating the square plus sine wave, that is a 128K samples get generated. Now you need to go to the folders, that is output folder, where you can see output generated files will be appear here. Tag output square dot bin. Now again go back to the SDK. Here you can see there's a tickle file where we are uh, basically downloading 128K samples data from file to the DDR memory location which to be played out of the DAC. So here I will source this tickle file, that is by using the command source download waveform.tickle. Download waveform.tickle is the file name. So after sourcing this waveform to the memory location, so what I will do now, I will play this data from memory to DAC via DMA. So that I can do by giving the DAC play command on the console window, that is Teraterm window. DAC play 256. DAC play 256 basically means it is a start playing the data from memory location via DMA to the DAC port. That is 256 is the amount of data we are playing. So right now we are playing the 128K samples, so that is in the integer format. So it is like 128 into 2, because 2 for each byte of the data. That is 256 kilobyte of the data we are playing from memory to that. Then after some time you need to give the ADC capture command. So ADC capture command capture the amount of data received from the ADC output into the memory location. Now you need to capture that received data from memory location to the bin file. So you can give the source capture.pickle command. So output files will get captured in our system from memory location to system. At the end, you need to send the command DAC stop to stop the playing the data from DAC to ADC. So here you can see we have an output file, that is a cap square.bin. Now you can go back to the MATLAB to see the waveform. So here I can set the output file, that is a cap square.bin, and then run the MATLAB. So here you can see you received the 128 kilo samples of data that we transmitted. Here amplitude got minimized, that is we got the minus 9 dBm loss when we transmitted from DAC to ADC end. So in the same way you can capture the large amount of data also at the output end. So for capturing the other size data, other amount of size of data, what you need to change? So first you need to go to the capture file. Here we have 131072 set, that is a 128 samples K samples. So if you want to capture 256 K samples, so you need to just copy it over here. And you need to change this size, that is 256K samples you want to capture. So you need to insert the size, that is amount of samples you want to capture. So just change it for 256K samples. And comment out the previous line. So 256K samples means 262144, and again for the 512, that is 262144 into 2. So you can change the file name also to just distinguish between them. So again, what you need to do, you need to give the commands. First, you need to give the source download waveform.pickle. Then you need to give the DAC play 256 KB, and then you need to give ADC capture. That is like how many samples you want to capture. So initially it was 128K, now it is 512K. So you need to give the command ADC capture. Five one two into 2, that is 1024. So by giving this command, it means you want to capture the 512 kilo samples of data from memory to our system. So now again, write source capture.tickle, then this file will get saved in your system. So now you can check this file by going to the folder where you have a file, all the received files. So you can see capture square 2.pin got captured. Now again you can go back to the MATLAB code. You need to change the number of samples. That is, initially it was 2 to the power 18. Now you need to change it 2 to the power 19 and then change the file name. So here you can see the waveform. So just for zooming the waveform, you can go to the access properties and just change the from the samples initial sample value and end sample value to check the required waveform accordingly. Basically, you can see main advantage of using DMA is like you can capture the large amount of samples at ADC in. Sample size can be changed up to the available memory size. That is, right now we have a PSTDR memory size is 4 GB. So whatever we have a available memory size, we can capture that much amount of data using the DMA-based design. So here you can see we captured the 512 kilo samples of data. So by through this you can verify it. So again go back, and then if you want to capture the 102K samples, then again you need to copy this command line and then put it over here, 1024K samples, and then you need to give the MRD command signal, and then you need to change the size, how much amount of samples you want to capture. So that is 1024 into 1024, that is 1048576. Then save this file. Again go to the SDK. So you can source, we are sourcing the again waveform to the DDR memory. So this is like source download waveform.tickle is like optional step if you want to capture continuously. So once you will give the source capture waveform.tickle command, download waveform.tickle command, then directly you can capture, like giving the ADC capture command from the Teraterm window continuously to capture the more number of files from here. So for 1024 you need to give ADC capture 2048. So in the same way you can verify it through the MATLAB. So you can verify it using the MATLAB. So you can see the output waveform over here. Or 1024K samples. Now just go back to the SDK, then go to the SRC folder. You can see different C files. Then you go to the main.c file. This is the main HTK code file. So as you can see over here, so all the command is written in this C file to just make it work. So starting from here, you have a display IP version. So on the term window, when uh, FPGA is programmed, then you can see at the top, that version will appear initially. That is IP version, major version, and after that you can see configuring the data converter files. So here I'm having a function call that is lmk04208 configuration, that is 10. So this is configuring my reference clock, and then we are setting the clock sampling frequency, that is a DAC clock and ADC clock. So right now we have 1.47456. So this is my LMX259 for configuration function call. So this is my configuring the clock, and then we have a different commands over here. So now if I will go to the clock.c file, you can see we have a clock configuration LMK4208 file is defined for the different values. Same for the sampling frequency, also different registers values are put it over here. So you can select any of the frequency that is mentioned here. Now this play DMA.c is basically showing the transmitter DMA part, how we are writing in the transmitter buffer of the DMA, and then we are sending the data through BDs. And then this capture DMA.c code explains the receiver setup, how we are receiving the data in the receiver buffer, and then writing to the memory location. So now I will explain the code in elaborate in my next video. So now coming back to the block design, as I discussed earlier, how we can set the different sampling frequency rate. So first, just open it, then go to the RF data converter IP. So here we have a RF data converter IP, and you need to double click on that. So once it will open, you need to go to the system clocking. So here you can set the sampling frequency over here. Then this is the clock out, that is 184.320 megahertz. Now again go back to the SDK, go to the main file. So whatever sampling frequency you set in the Vivado file, you need to change here also. That is LMX2594 clock configuration command. You need to give that particular frequency values over here. And apart from this, you need to go to the folder in the clock files. Here you need to put that register value file, changing the clock. So that three things you need to do. First you need to change in the Vivado, then you need to change it in the SDK code, and then you need to put that file in the clock file folder. So that's all for running the design. This is my references. Thank you.